Thanks guys for
yeah, no problem. I'm so sorry for all the problems there. Getting caught up, I think, in the initial hiccup.
You will be the next. Okay, so in this study we are focusing on hypergolic system. So the hypergolic propellants have been widely used in rockets and aircrafts. So typically the hypergolic propellants consist of fuel and oxidizer. So traditionally, hydrogen and hydrogen derivatives can be used as fuel, and the nitrogen dioxide can be used as oxidizers. So when these two components are contact, there will be spontaneous ignition, even at room temperature. So the hypergolic reactions have been studied in the literature, but it is from the barrier height, it's like 0.4 electron volts, so which is very high. So it is unclear why the hypergolic reaction happen at room temperature. So in this study, we want to figure it out. So another thing is, so traditionally, classical path approximation is used as basis for computational calculations. But if hydrogen motion is involved in chemical reactions, then CPA is not safe anymore. So we need to remove this approximation. So in this study, we first use DFT-based ab initio molecular dynamics to simulate the chemical reaction of monomethyl hydrogen with nitrogen dioxide. From AIMD calculations, we can get ab initio potential energy surface. With this potential energy surface, we can use it as an input to run additional nuclear wave packet dynamics calculations. So the take-home message is quantum tunneling is responsible for the hypergolic reaction for this system. So here I'm going to skip the computational details. So this result shows the chemical reactions in the early stages of AIMD trajectories. So here, these three panels corresponding to three sequential steps of hydrogen transfer. So this is the first hydrogen transfer reaction, like I show here. And after three sequential steps of hydrogen transfer, we end up with this kind of compound. So from this energy diagram, we can identify the barrier height. For example, for the first hydrogen transfer reaction, the barrier height is about 0.5 electron volts. So the barrier height is just the energy difference between the reactant and the least stable intermediate. So this table here is the results for beta charge analysis. So the point is to show the hydrogen being transferred is actually proton instead of radicals. And these two panels shows the number of different species in the AIMD trajectories. So basically, in addition to the three sequential steps of hydrogen transfer, we also observe other chemical reactions. For example, we observe the breaking of a carbon and a nitrogen bond. So here, I use some simplification and also some mathematical operators. We can just convert the energy diagram to this one-dimensional potential energy surface. So in this diagram, the vertical axis is energy, the horizontal axis is a reaction path. So this diagram can be used as input for nuclear wave packet dynamics. So our ab initio molecular dynamics is run at a very high temperature, like 2000 Kelvin, but our nuclear repacket dynamics can be run at various temperatures, even at low temperatures. So here I show an example. This is a repacket dynamics at room temperature. So here's the red, this is the initial state, and the green, this is the final state. So initially, the center of the Gaussian wave packet is at -1 atomic unit of position, and as time goes by, the nuclear wave packet move towards a positive direction. So finally, we can see some wave packet passes through the barrier, but majority is just reflected back. Okay, so here is another picture showing this process. So this is our initial, and as time goes by, at around 240 atomic unit of time, we can see the splitting of the wave packet. So from this diagram, we can see about 20% wave packet has passed through the barrier, and about 80% has reflected back. So here, this diagram shows fitting for the reaction rates. So, like I said before, the nuclear wave packet can be performed at different temperatures. So here, each point corresponding to a specific temperature, and from each run, we can get the reaction rate. By using this reaction rate, we can fit into Ramirez equation. So from Ramirez equation, we can get the parameters like A prime, B, and C. With this, we can get the Ramirez activation energy. So the Ramirez activation energy is temperature dependent, but at room temperature, it is about 0.03 electron volts. So the activation energy from Ramirez equation is much lower than the barrier height in ab initio molecular dynamics calculations. So my result is first AMD calculations can be used to capture the chemical reaction of this hypergolic system, and also through the wave packet we can say the hydrogen channeling is responsible for this reaction. That's it.
Okay, but thank you. Any questions, conceptual or about organization?
I just want to know what that natural log over K,
Yep.
top right one, yeah, that one. So K in this case is the rate of reaction, right?
Yes.
So so the rate of reaction goes down as the temperature goes up, or am I reading that the other way around?
Daniel, can you read what is axis for this figure?
1000 divided by Kelvin.
Divide by Kelvin.
Yeah.
So, in which direction temperature growth?
So this part is the room temperature.
Okay.
So this is high temperature.
Oh, sorry. Thank you.
More questions? If no, then thank you once again.
Okay.
Aaron, would you be interested to tell a story about your proposal?
I can say something. Would be great.
So, if you are working on the similar projects, do not hesitate to borrow some ideas. So we interact with each other with two purposes. One, that each of us in the audience serve as a reviewer to help the author. And on the other aspect, we all are learning from the author to improve our own research.
There's zoom option on this.
Huh? Zoom? Zoom?
Control plus.
Or maybe rolling the mouse.
Control is scroll the
No,
mouse.
mouse scroll. Control plus minus. So lead halide perovskites have been pretty popular material over the last decade or so, and different morphologies have become popular in different subfields. So, I'm looking at lead halide perovskite nanocrystal, and specifically we're looking at transition metal doped lead halide perovskites because, well, I mean, so perovskite quantum dots are cool, like on their own, like they're very good light emitters, but over time they can become unstable. And one way to try and increase the stability is to put things inside of them that will emit light. So eventually you can use like transition metals to be the emitters in different materials. And recently, a couple years ago, people have been exploring Mn2 or manganese 2+ dopants into these perovskites because lead takes a 2+ oxidation state, so they're pretty similar in that respect, so they should substitute. And experimentally, it's been observed that they resemble something resembling a spin flip transition from a triplet to right word, 3/2. Can't remember the word.
3/2.
3/2 spin.
So
It's quartet, quadtet.
yeah.
So spin flip from a 3/2.
2/2
Yeah.
triplet, and then the next one 3/2 from the quartet.
Basically transition from a 3/2 to a 5/2 transition. So what we try to do in this work is to model the electronic structure and the excited state dynamics for these systems, and to look at the possibility of spin flip transitions in these. We have to use a more sophisticated methodology than what's typically used. So we use spinner cone sham orbitals because with spin orbit coupling, that facilitates the spin flip for transition metals. So if you don't have spin orbit coupling, you can't model spin flip transition. So we include that into our methodology. And I didn't highlight it earlier, but this is our model up in the top. So it's our perovskite quantum dot, and then in the very center it is doped with a transition metal, and it has a bromine halide field around it. And these are just some equations we use to compute the observables in these systems. So for ground state electronic structure, I already mentioned we use spin orbit coupling, and those give us cone sham spinner orbitals. So superposition of spin up and spin down. And we take those and we use these as a basis for ground state observables. So two most prominent ones to look at is density of states and absorption spectra. And we compute those using transition dipoles. And then we also use spinners for excited state dynamics. So we use spinners as inputs for our non-adiabatic couplings along a molecular dynamics trajectory. And then we process those into state-to-state rates. And generally we can model the electron-phonon interactions in these systems. So for results, for a reference, we first looked at spin polarized calculations for this model. And we found it takes a high spin configuration, so 5 unpaired electrons. And these two bumps here in the middle of the conduction and valence band are hybridized manganese states with the halides around them, which is shown in the PDOS below. So this unset here shows that it's roughly 50-50 percentage of manganese D orbitals bonding with halide P orbitals, or the bromine P orbitals surrounding it. And we do see that in the conduction band there is some valent D states that are hanging around just around the conduction band edge, which is a good sign because if you're trying to get photoluminescence for the materials, you want those D states to be near the band edge, so that after non-radiative relaxation, the electron occupies there. But when we go and do our spinor computed ground state electronic structure, we still see that we have these two D states in the middle of the gap. And then when we look at our PDOS, we see that the Mn2 plus states that were originally at the conduction band edge, they get pushed deeper into the valence band due to strong spin orbit coupling of the perovskite p orbitals, which reduce the band gap. So basically, we have the wrong energetic alignment for spin flip transitions. If it is the case that it is D to D transitions that are observed experimentally. So using the GGA functional with spin orbit coupling, we can qualitatively get the right valence band electronic structure, but for the conduction band, it's not as well. It doesn't work as well. And below that is just some pretty orbital plots to go along with the spin polarized density states. So you can see, so for the states that are within the gap, you can see that those are D orbitals. This is some sort of DXY hybridized with the P orbitals around it. And this is the DZ orbital, DZ squared, that hybridized a little bit with the surrounding ligand field.
Did you label it, or you just giving labels from the top of your like knowledge and memory?
That's mostly memory.
Okay. It could be reasonable to label.
Mm-hmm. And then, yeah, once you go into the conduction and valence band edge, it's more perovskite quantum dot states, or it's delocalized over the entire nanoparticle. So,
why does it have a different background color? What does it mean?
Is it intentional, or you just it's technically difficult to keep the same color?
Yeah, it's technically difficult. It's just from the software because it's a slice. So if you imagine you take your parchar orbitals and it just slices through them, so the background just changes depending on the other orbitals that are around it. So the important thing is just the contrast. So we trudge along even with the qualitatively incorrect valence band. We can still go through and try to compute the DED transitions. And these, so here in this big plot is an absorption spectra comparing the spinor orbitals, which is the solid red line, and then the spin polarized are the dashed orange and green. And so the big thing the takeaway here is if we zoom in on these low energy transitions, which are about an order of magnitude less than like absorption from the perovskite quantum dot, we see the lowest two bands. Those are Mn3D to lead 6P transitions, and that's just confirmed from looking at partial density states. And then once we get up to around 2.2 eV, we do see that we can see DD optical transitions computed from the transition dipoles from the spinners. And then, yeah, then this diagram is just corresponding to the absorption spectra with each labels corresponding to the ones in the table. So for E and F, that's from perovskite band edge to MND state. And then this D is from MND to MN state.
Is it good or bad, and how does it compare with experiment?
The energy of transition for the lowest transitions compare favorably well to experiment. So what they see in experiment is around 600 nanometer, so that's about 2 eV. So it's, I mean, when I was first doing this, like, it looked like a duck, so it had the right band gap, the right transition energy, which you'd expect, but it's either, well, I guess it's unknown because in experiment they just infer that the PL they see is from the manganese dopants, because it's traditionally, if you have the so-called Forde A1 transition with the manganese dopant in there, it's like you just assume it's that transition.
A question. So, if for an intrinsic perovskite with no dopants, so does the basic electronic structure looks reasonable by using PPE plus SOC?
Yeah, so you get, so with perovskites you get qualitatively correct band gap. Well, I take that back. If you don't use spin orbit coupling, you get qualitatively correct band gaps for like the size of the material you're looking at. So this one just happens to look experimentally correct, just due to the spin orbit coupling. So having the correct band gap is kind of just an accident. A nice accident, but so then, yeah, that was its retrospector. So now I'm going to move on to modeling excited state dynamics in these systems. So like I said earlier, the conduction band isn't very reasonable to compare, like, or what's the word I'm looking for? If we assume that the electronic structure is not correct, it's like we can't really gain any meaningful information from the dynamics of there. So mostly I'm going to focus on the dynamics of the whole transitions, because it seems like we can model those qualitatively, are pretty correct. So what I did is I just compared the spin alpha, or the spin up electrons, which contain the states within the gap, to the spinner non-radiative relaxation. And so the red field tensors basically just control the rate relaxation from one state to another. And once you put in an initial condition, these just tell the state how to relax to the band gap. So for both the systems, I chose initial conditions which were roughly equal in energy. So for the whole transition, it's about 1 eV separation between HOMO minus whatever I chose to the HOMO. And you can see that there's quite a wide variation in the relaxation time between those two. So this is on a log plot, so we can see for the spin alpha component, it relaxes to the band gap like under sub-picosecond, whereas for the spin orbit computed relaxation, it's above 10 picoseconds, edging up towards 100. So it's almost like a 2 to 3 orders of magnitude difference in the whole relaxation, just based on computing with the different bases. So, and then these plots just kind of show how the population relaxes in time. So you can see it's a very quick relaxation from pretty much each state all the way to the HOMO. Whereas here there's like a bottleneck that happens from around HOMO minus 2, HOMO minus 1, then up to HOMO. So I didn't exactly figure out what's like the physical reasoning behind this, because with spinners you can't really compute orbitals for them, so you can't compare orbitals from the spin alpha with orbitals from the spinner. But I would suspect that with spin orbit coupling, that tends to shrink your orbitals due to faster motion. Like it contracts your orbitals. So if your orbitals are more contracted, there's going to be less spatial overlap for it to be non-orthogonal. with it. So that's the best idea I have at the moment, but besides that, I haven't been able to think of a good reason for 2 to 3 orders of magnitude difference. Because the energy offsets between all the transitions are basically the same. So it's not an energetics thing, so it has to be due with the overlap of the orbitals along the trajectory. So that's still kind of a mystery.
Is it possible that there is some difference in the charge density distribution in the intermediate states?
I don't know about the intermediate states, because you see, if you look at the, like this waterfall plot, you see in the intermediate states, it's like they even, appears like the rates of transition are even quicker, like further away from the gap.
Huh. So the long dynamics that you are blaming happens only between 2 lowest states,
Right.
like Luma and Luma plus 1.
It's the D to D transitions pretty much.
Hmm?
And then, yeah, the d orbitals are going to have, they have a spin orbit influence. So if you include spin orbit coupling into the basis, that might make them more orthogonal to each other, or it's a better basis to describe transition metals. It's a really hand-wavy argument, but it's the only one I got.
But if one would explore spatial distribution, then for the last 2 states, this Luma and Luma, whatever, what is the
HOMO minus 1.
HOMO minus 1 and HOMO, the charge density will, in both states, it stays in the same region on the doping.
Mm-hmm. Yeah, they are. From the PDOS analysis, they're still both the orbitals I was showing earlier. So it's still these 2 states, and it's roughly the same hybridization.
Mm-hmm.
So it seems like so this is with the spin polarized basis. When you include spin orbit coupling, they become more orthogonal to each other. Because that's one problem with GGA functionals, it's your orbitals tend to over delocalize. So spin orbit coupling, and you can think about it in some ways including like exchange correlation effects too, to correct the orbitals.
Did you take a close look at the PDOS? So what is degree of hybridization for these 2 atoms?
It's about 40% metal ion, or manganese orbitals, about 40% bromine P, and then the other 10% is either ligand or s orbital, or PBS. I guess it's a higher, well, just looking at the image you can tell, that's for the topmost state. This one, it's more like, I think it's still 40% of the bromides around it, but it's less of the D metal. So, yeah, still kind of a puzzle right now.
And it is the main conclusion.
Yes. We are still puzzled.
Okay, it's good for science. Just stay puzzled.
Keeps me in a job. So, then speaking of exchange, correlation, and different functionals, excuse me, so some work within the last couple of months is seeing if there are different methodologies to get the correct band alignment, assuming that you need both your D transition metals to be within the gap for conduction and valence band. So one study we did was using DFT plus U with spin orbit coupling and just systematically scanning U parameters. And short story is if you include, like, the bigger you choose your U, the worse the result is, or the higher it pushes the D metals into the conduction band. So that did not work. And so we've also tried a couple of different hybrid functionals. So the first class of like quantum dots to be doped were like the cad selenide, zinc sulfide types. So those have been the most explored ones for modeling. And it seems like PbO0 was the best functional to model the d orbitals in those systems. But when we tried that for our system, we got worse results than with the GGA. The valence band d orbitals were pushed inside the gap, or pushed into the band more, and same for the conduction band. While with the SHE06, which isn't fully done yet, but it's only needs a couple more steps to converge, you can see that, well, I didn't multiply the dopant states, but there is a hybridized dopant state within the gap. And it's hard to see, but in the valence band, the dopant states are hybridized with like LUMO +3, LUMO +4. So it's not too far from the band edge. So it seems like looking at functionals which include more of HSE character describe these systems better. I'm not sure exactly why, because I'm not sure of the technical differences between all of them. I know they include different amounts of the Hartree-Fock exchange and some other different parameters, but I'm not exactly sure why one functional, or why the HSE works better than PbO. So conclusions for all this work is we're able to successfully compute spin flip transitions in these systems from looking at the optical spectra. You can see the D to D transition. For non-radiative hull relaxation, it was slowed down by 2 orders of magnitude using spin orbit coupling compared to spin polarized calculation, which we attribute to spin orbit coupling being a better basis to describe transition metals. And more work is needed for screening functionals that can accurately model both conduction and valence band for doped quantum dot or doped perovskite systems. So that is it.
Okay, let's thank Aaron. Any questions or suggestions?
I have a technical question. So for your DFT plus U calculations, so you only modify the U term, right? Did you play with the, I guess, J term?
J.
Yeah.
Well, I didn't do the calculation myself, the collaborator did. I would have to dig around in the directories that he did, but it doesn't seem like it because the way he labeled the folders, it was U0 is U1, U2, U3. So he must have kept J constant, unless he just changed it with each one, but I doubt it.
Because it seems you need to find the combination of the U and 2.
Yes, you're correct. Okay. More questions?
What made you choose those specific full relaxation? Like your HOMO -15, your LUMO +5? I was trying to see why you chose those specifically.
I chose them based on to get like an accurate comparison between the relaxation. So I chose so that both of these, like if this is delta E, that delta E for both of these was about the same.
Oh, okay.
Because like if you assume it follows like a ring law, it's like your initial condition will affect that. So you want them to be both the same.
More questions 1? More questions 2? More questions 3? Let's thank Aaron once again. I had a question why you didn't show photoluminescence, but maybe luminescent you can.
It wouldn't fit.
If it is only the reason, try to fit, because it can fit because we are allowed for 4 feet.
True. Well, that and I didn't want to display the 0.05% quantum unit.
Yeah, it is, yeah, because you create really great impression by your oral presentation with high pure quantum unit, and then on poster you can discourage people. Yeah, I would like to invite the author of this nice poster to the stage. And if you were making comments for Aaron or Daniel, please share your comments with them.
Yeah.
Silicon nanowires have some intrinsic properties such as one-dimensionality and high surface to volume ratio. So it's a special class of nanomaterials, and they are included in solar cells, lasers. So the electronic properties of silicon nanowires have been studied theoretically already, but it does not include multiple K points, and we know that periodic solids needs multiple K points. So in our previous study, we studied electron dynamics on different silicon nanowires, but we did not include multiple K points. So now in this research, we studied K result dynamics of two different silicon nanowires, silicon 001 or 100 and silicon 111. Here you can see this. Here you can see the dispersion curve of two different nanowires. Actually, I calculated dispersion curve for 16 different K points and 4 different K points. So, and then it is appeared that I didn't include 16 K points dispersion curve here, but if we compare both of them, we can see the states, shapes of the states are pretty same. So we decided to stick with 4 different K points, and for each K point we need to deal with around 1,000 coupling files. So 4 K points is good. If we include more than 4 K points, it would be computationally expensive. So here we can see the models, like a top view of two nanowires models. And here we can see the transition. This is direct transition and this is indirect transition, but it is for optical transition to excite the electron from valence band to the conduction band. Here we can see the kind of zoomed in image of this portion, conduction band of silicon 100 nanowire. And here we can see there are 2 kinds of transitions. One is at the same K point, and another one is 1 K point to another K point. So same K point transitions are direct transitions, and transitions between 2 different K points are indirect transitions, and these are non-adiabatic transitions, by the way. So there are 2 transitions, optical here and non-adiabatic over there. Now I'm going to talk about the methodology, what method was used to study this research. So we considered molecular dynamics trajectory for calculating the on-the-fly electron to lattice coupling. Here the main equation is one electron constant equation, and this is the solution of this equation. And we can see this wave function is dependent on k points. So if we excite electrons from valence band to conduction band, and when electron come back to the band edge, it couples with the nuclear motion, and it includes different time steps here. So here we can see the time dependency, but this is not here. And then this is the coupling equation. Here this wave function is at k point, and this is at a different k point, k prime, and at different time steps here. So since momentum is not conserved, so k prime is not equal k. Once we have the couplings, we can calculate the autocorrelation function from the coupling equation, and if we have autocorrelation function, so you can get rates of transitions from the Fourier transform of autocorrelation function, and then those rates of transitions are the component of rate field tensors. And the time evolution of density matrix equation is here, and the second term on the right hand side is the electronic energy dissipation, is for electronic energy dissipation. So here this equation is for non-equilibrium charge distribution. And here this one is for equilibrium charge distribution. And then we can see the expectation value of energy is a function of energy and time.
Good. Keep going.
And then we can, the rate of relaxation we can get using this equation, by fitting this equation, and this is just we solved for rate of relaxation from this equation. Now I'm going to talk about how to select initial states for dynamics calculation. In order to do that, we used MATLAB code, and since we know we need rate field tensors for calculating dynamics, so we used same MATLAB code for calculating rate field tensors. And
I have a question. So what's the meaning of a MATLAB code to a stranger?
what was that?
So if there is people from outside, what's the meaning of MATLAB code?
Then I would say that we just used a perovskite.
But
Do I need to include that? I don't.
no. Which equation or set of equations is solved numerically in MATLAB code? You can point like, here are the equations, and we are not solving them analytically as in differential equation forms, but we just use numerical propagation or whatever.
Okay.
But point out which.
So it's a rate field tensors equation.
Just point which equation.
So this equation.
Once again, which one?
This rate field tensors.
But it is the code for correlation, right? And the dynamics is solved in which code? For dynamic, when you run for dynamics, which equations are being solved?
Dynamics. Charge distribution.
No, it's observable. Higher up.
Oh, this equation.
This two, this and the next one. No.
This is one.
This and then where you see time derivative of density.
Yeah.
And yes, and the next line.
This one.
Yes.
Then I will-
So it is basically one equation split on two lines.
Yeah.
And it is main equation that is solved numerically in the code.
Okay.
Right?
Okay, since we have 4 different key points, so we have 4 different energy profiles, and
Last question, what's the meaning of energy pop?
it contains the states and the energies, and it contains number of states. Like we are interested, suppose if we are interested in 30 states below HOMO and 30 states below LUMO, so it contains those active states. So for 4 different key points, we have 4 different energy profiles, and how we combined all of them together. Yeah, and the name of the resultant energy profile is this one, and this is the format. Like it is one part of resultant energy profile. Here we can see how the energy states are arranged in the resultant energy profile. So this is for LUMO for K.1, and then for LUMO for K.2, and then 3, and then K.4, then LUMO plus 1 for K.1, and it goes this sequentially. And for dynamics calculation, we would consider this LUMO is, this one is initial state 1 for K.1, this one is electron state 2 for K.1.
What is the
Sorry, please go ahead.
what is the energy here, energy column?
Energy this.
Yeah, what energy it is? It is
In energy
transition
of that
energy or
state. Energy of that state.
Can you show it on your diagram because you have
Yeah, here.
Mama,
Okay. So energy of these states, like if that is gamma
okay,
column.
so this is
So what both Yulun and Jabet were trying to say, what you are telling is absolutely right, but you are using colloquial language that we developed inside the group. People outside will not understand.
Energy pop, they will not understand.
No way.
Okay.
So you need to use standard, and even the word states is not very appropriate. You should tell like band or orbital. Band is better word. So each band in the band structure is distributed by several discrete points, and we inspect its energy, and then look how the occupation goes between this.
Okay, I was thinking this not standard name. Yeah. Okay. Here, on top of this, so I split. I put 2 columns here, one for silicon 100 and another for silicon 111, and I put the relaxation rates for 5 different states at gamma point only, and since the whole table will not fit it here, so I just placed gamma point states and only 5 states. But I did calculate for 10 states for each K point. And I know I need to edit this thing, like title of each column. And so I can calculated electron dynamics for LOMO plus 12, and in resultant band file, this LOMO plus 12 state is initial state 50, and it is for initial state 50, but it is for gamma point LOMO plus 12 state. And for silicon 111, it is the same way, but this time I considered initial state 40, that is LOMO plus 9 state at gamma point.
So band LOMO plus 9 with specific value of momentum.
Yeah. Mm-hmm.
Okay.
Okay, and then I calculated for each nanowire, for each K point, relaxation rate for 10 different states. And then I calculated the relaxation time from the relaxation rate, and then I took the natural logarithm of that relaxation time and made graphs. Then this x-axis represents the dissipated energy, the energy difference between the band state and that corresponding excited state. And the same thing for silicon 111 also. So in order to fit the these rates, by the way, these rates for how you can see the empty points, those for indirect transitions, like if electron transfer from one K point to the same K point, then we call it an indirect transition, and those empty points for indirect transition. And these field points for we would say all transitions, includes indirect, direct, everything. I mean overall transitions. And if we fit these relaxation rates, we see that for a couple of initial steps, it follows a gap law, and after that it follows a inverse gap law, and almost for all K points. On the other hand, the same thing. So I should put a gap law and inverse gap law there. So, and then what we did, we calculated the transition difference between direct and all transitions. So we saw the transition difference. It is pretty constant for 3 different K points, and for 1 K point for 0.5, the change is linear. For silicon 100 nanowire. For silicon 111 nanowire, we see that for 0.16 and 0.13, for these 2 K points, relaxation rate, the difference between relaxation rates are constant, but for the other 2 K points, the change is, the difference is linear. Here I put how electron, there is a movie, but I took the snapshot for first initial, and this is intermediate, not the final. This one should be here in the final state. So how energy changes with momentum, you can see from these 2 figures. So this is the trajectory of electron is coming to the band edge. And this is the same thing. So probably I need to put the states from where it started. Okay, I remember this one is from 23 long plus 3 for K point. I don't remember exactly, but I'll put the initial states number here. And so this is the same thing, like how energy it changes with momentum here. This is the same thing, like I took the snapshots from initial and the final states. And then I need to put at least two more figures, how momentum changes with time here.
Why? What are you going to prove with these figures? Yes, that momentum changes with time.
Okay, here is a summary of the outcome of this research. So the conclusion is indirect transition is quicker than direct transition, since not indirect. I should correct that one. So all transition is always quicker than direct one, because in all transition there are more pathways to relaxing. That's why. And so we saw that for first couple of states, a relaxation rate is following gap law, and after that at higher energies it follows the inverse gap law. And I would like to acknowledge Javed. That's all.
That's it?
Yeah.
Okay, well, thank you. More questions?
I have a very stupid question about the green background color. I guess maybe it doesn't make sense. So why you have the green background color figure?
This one?
Yeah. So why you have this specific?
When in MATLAB code, the plot it was selected certain category. It might be different color. It is a different category.
I don't care about color, but why you have this specific trajectory?
Oh.
Can we do? Is it possible?
You
we
mean
can
the
do?
trajectory means this path?
Yes. Can we do like directly transition first, and then we do indirect transition?
Yeah, we can.
Well,
Yeah, we can do that.
I think the whole point is to enable simultaneous change of both energy and momentum. As soon as we depart from quantum dots and molecules as we go into solids, the change of momentum becomes reality. It is a natural effect that can take leading role, and we do not know. We cannot assume before we start calculation what happens first: to relax a little energy and then change momentum, or first change momentum and then relax, or make them simultaneous. So
yes, that's my point. So basically, we have a starting point and we had an end point, right? So what we are doing right now is to find the best road.
I understand your question. You are thinking like in theoretical mechanics with Lagrangian, with least action path.
Right.
No. Here, Fatima sets up only initial condition, initial point, and before the dynamics has been run, one doesn't know where it will end up. So one not only optimizes trajectory, one also optimizes the endpoint. One can intuitively predict where it will be. So it should end up at the minimum of the dispersion curve. but who knows? Maybe sometime it will end up in different point. And if you look, Fatima, can you finger on the rightmost green figure?
This one?
Not left, right. Next.
Oh,
Yes.
okay.
See, there are 3 orange points.
Mm-hmm.
So the end point of trajectory is equally distributed between several values of momentum. More questions to Fatima?
Can you like waterfall these or make waterfall plots? Or is it possible?
Of green things?
Yeah. No, about these trajectories.
Maybe.
No, because it seems strange to me that even with like that, because the trajectory that the left one follows, it ends up at a point where the energy spacing is larger. So it seems odd to me that overall that route is significantly shorter than one that's momentum restricted. That makes sense. So I just wondered, like, if there's like a buildup of population at that point as it's trying to relax, or if it's just happens to be a quick route even with the sizable energy gap.
So what you're suggesting is to, instead of making snapshots of the distribution, to make a waterfall to show the dynamics, right? But it is not possible. At least I don't see how it is possible, because in all our previous, can you focus on higher part, upper part of the poster? Yes. I don't know if I will have time to approach your poster and help during formal presentation, but so here you can do one-dimensional curve at each point of time and make waterfall figure. So Aaron is asking, is it possible to show dynamics, all intermediate states in the poster? So here we have several intermediate states, the whole profile of dynamics. But if we are coming here, this is one-dimensional distribution with time as a parameter. One-dimensional with one parameter. Here it is two-dimensional distribution with time as a parameter. So at each point of time, this is not point. It is kind of Gaussian distribution with shape, and it moves at average position and it changes its shape with time. So it would be not waterfall, but one can represent it same as medical tomography. Slice of two-dimensional distribution at each point of time. So it is slices.
Yeah, that makes sense. There's some way to characterize the populations of states at each.
And visualization of calculations that Fatima is doing is a really big challenge, because before everything what each of us were doing, it was taking like several orbitals at different energies and follow occupation of each orbital as function of time. And here is additional dimension. For each band, for each orbital, there are replicas with different values of momentum, and they are additional. We do not know which word to use, states. So if here there were like 20 orbitals, and she is using like 4 K points, it is 80 states instead of 20. And one needs to follow population of each of them. So it is really breaking minds and hearts. Are you satisfied?
Yeah.
Good. More questions?
Maybe just one comment. Instead of referring to as all transitions and direct transitions, maybe something along the lines of like momentum restricted, momentum unrestricted.
Good.
Because I think that would come. It's more intuitive, at least for me anyway.
Did you write it?
I was in the process.
Okay. Please join me in thanking Fatima once again. Please collect feedback. And we should have two more in the remaining. Can you please resend it to dmitry.kivan@gmail.com? Javed, can you quickly over your poster while Landon is sending email?
I want to
Just entertain us with example of good science. And there is only one copy of Javed's form, so one can pass it around and make it.
You want it on your NDSU email?
no Gmail.
So
Okay,
you will start and
that's the one that I sent you before. At Gmail.
So this is my second poster I'm going to present on the SES, but my apologies, actually I'm not complete. I didn't make anything yet. So this is my old poster. So I'm going to take a lot of stuff from the old poster. So since I supposed to present today, I just sent him the old one. So this is on my work on the silver cluster. And this silver cluster, we are interested in silver cluster because small silver cluster has a very diverse and photophysical properties which can be applicable in the in biological sensor, or especially in more biological sensor type applications. So problem is, in this case, main purpose of using of silver cluster is when the silver cluster becomes smaller, like 10 or 20 atom size, less than 20 atom sizes. So its photophysical property is completely dependent on the conformation of the cluster as well as the interaction with the nucleotide. Since it will change the photophysical absorptions or emission based on the interaction of nucleotides, so this type of cluster can be used in biosensor because in specific interaction with a specific DNA or RNA, it will emit the specific wavelength of light, or it will show the specific absorption spectra. It's known as a structural absorption phenomenon. So that's why we are working on a smaller size, like less than 10. But in this paper, I'm going to show mainly the monomer and dimer of the 5 and 6 silver cluster. 5 and 6 means 6 silver atoms and 5 silver atoms. So it's very, very small sizes. And although it is small size, but its conformation can be changed due to the, as I said, interaction with the DNA RNA. We know that DNA has a backbone chain, so it's not that flexible, but so due to the interaction with the nucleotides, specific nucleotides, based on the 3D conformation of the DNA, it will give you the different conformation of silver cluster. And from the experimental group, and this is also a collaboration from the experimental group, our experiment, they have a lot of extensive work, but one of their finding is they found that, and when they formed the monomer, and now with the time, by changing the pH and something experimental setup, this monomer can form a dimer shape. But they are not sure about the conformation of monomer or either dimer, either one. And thing is, if you look on the absorption spectra, this is experimental absorption spectra. A red line is showing the absorption spectra of the dimer, and black line is a monomer. They saw that whatever the size of this cluster, when they form the dimer, the lowest energy peak is going to diminish, is become a dark peak, and the second absorption peak is increases the intensity specifically, and the third one is going to lower intensity than monomer in that case. So we started with these experimental results. We tried to figure out the conformations or mechanism of the dimer formations. Since we don't have any spectroscopic result, we started in the very beginning or very
we have a lot of different degree of freedoms to make confirmations. We'll make a confirmation of that one. So in primary cases, we started with the lowest bare silver cluster confirmations, and then we ligated with the say cytosine mainly, and mixed in another study we started with the cytosine mixed with the guanine. The reason of the using cytosine mainly because most of the experimental results they show that they have shown that they have found the emissive cluster when they use the cytosine rich nucleotides. And there are some other studies they also found that this intensity, absorption intensity or emission intensity could be increased by introducing the guanine, but only guanine rich nucleotides is not emissive, but it's increased the intensity when it started with the cytosine. But they have no explanation of why cytosine is emissive or how guanine is increasing. This is just empirical result is intensity, but they don't have any concrete explanation of that. So we don't trying to explain that one, but we use that. That's why we used guanine and cytosine in our system. So we take a planar geometry of 5 and 6, and then participated with the cytosine and guanine and optimized. We found out the optimized silver 5 and silver 6 monomer. So if I look on the first study, first part of our study, this I'm showing the 3D confirmation of the cluster based on their charge and their ligands, how they're changing. So this one is example for the optimized silver 6 cluster. So if you look at here, this as I said, confirmation is very important in this case. That's why I'm showing the confirmation over the final confirmation of the cluster. This one is optimized with the all cytosine, only cytosine. So if you look, we started with the planar geometry, and after the optimization in the solvent medium, it's keep almost planar geometry. If you look at this one is a little bit tilted, but it's keep a more symmetric structure. And this one is a little bit distorted from the planar because of repulsion between the cytosine cluster. And this one is a charged one. And if you look at charged one is completely changed the 3D planar conformations. It's become a 3D one. But if you look at the silver 5, this one is a guanine one, cytosine one. This one is still retain the planar one, and also, but in this case, guanine 1 and 6 is completely distorted from the 3D. It's because of guanine nucleotide. Guanine nucleotide is larger in sizes, so they have a steric repulsion with the cytosines, and it's distorted to the 3D conformer from the 2D conformations. And the effect of this one, if you look on the absorption spectra, this one, they have a 4 panel. This one is these 2 panel for silver 5, and these 2 panel for silver 6, and the top one is neutral, and in both cases, this one is a charge one, 1 plus charge. And in this case, this black one with the cytosine, 5 cytosine, red one with the 2 guanine, 3 cytosine, and blue one with the 5 guanines. They have all with the same pattern. And the first one, if you look at here in the neutral one, is showing that when you add 2 guanine, it increases the distance, increases this peak, and is decreasing the intensity of this peak. But in case of 5 guanine and 5 cytosines, this peak intensity is almost same. So, but in this low energy peak, there are a couple of peaks here, 2-3 peaks in this. This one is the main peak. These peaks are because of doublet conformations, and this is the usually is dark, is not emissive, in this case doublet transition, and they have, it's also combinations, it's also a mixture of DD transition with the silver to ligand transitions. I am showing NTUs in the later on. And this one is a charge. Because of this multiplicity, lowest energy multiplicity is now singlet. It's also more stabilized, and this lowest energy peak is brighter compared to this one. But in this case, it didn't. This peak is almost is not changing with this changing of the ligands, cytosine or guanines. And another thing is, if you remember in the experimental one, we show their experimental group, they are mainly looking for reason of increasing the intensity of this peak, second peak, and the lowering the intensity of third peak. So in the silver, in case of silver 6, this is on the 1+ cluster, and these also doublet conformations. If you look on the second peak, this red line is a mixture of guanine and cytosine. It's increasing the intensity, but in other two cases, intensity is almost same. I mean, in the cytosine and guanine ligands, but in the mix of both, is increasing the intensity. But this one is also lowering the intensity compared to other one. So this charge cluster is giving us a kind of similarity, agreement with the experimental result. So, and also, since they are not sure about their conformation, and also there have some other support from the literature or the experimental work, that cluster formation, this silver cluster formation is initiated with by the silver plus, and the silver plus cation is agglomerates and making a cluster shape. So almost all experimental result is supporting that silver final silver cluster could be positive charge, is not a neutral almost. So our silver 6+ is showing the more agreement, and is also cationic cluster. So we assume that it could be probable the stable cluster in this case. And this is showing NQs. So as I said, it's showing the transition nature. This one is like mostly D to T transitions, silver transitions. But I had one question one time I faced, is the contribution of S to D transition and D to transition. I don't have a specific answer, but I'm going to include that in my new poster. I calculate this one. And the main peak, the highest intensity peak, this is the main contribution is coming from the ligand, silver to ligand transition. So that's why this from the NTOs is one of the fact clear that the bright transitions is mainly coming from the ligand charge transfer. So ligand is playing the important roles, because it depends on the ligands, it will change the transfer rate, as well as it will change the intensity of the transition. So that's why if you look on the cytosine, there are more number of transitions from the silver to the ligands, and in case of guanine, they have almost no transitions. So, but when I add the cytosine with guanine, it's increasing the transition transfer, but specifically to the cytosines. So they have no transition to the guanine, but guanine helps to charge transfer to the cytosines. So in the next studies, I just form a dimer. In the dimer formations, as I said, they have no confirmed conformation mechanism of formation. So we thought that maybe they have it's not a direct dimer formations. They have a separate, and is forming a dimer through the pi stacking of the different ligands. So I consider the different ligands, and this indicating the ligand pi stacking. I formed the different dimer, and then optimize that dimer to look on the final structure. So one thing is we found that in case of they form the dimer in the guanine 2+, we saw that there are some interactions between this cluster, and ultimately we are getting nanorod types conformations. And the effect of this nanorod formation you will see on the absorption spectra. If this one is showing this one is not visible. Okay, so this line is showing that dimer formations, and this red line is a monomer one. If you look at these, because of this conformation, 1D conformations, it increases the intensity of this transition is very, very high. And the nature of this transition is, interestingly, is silver to silver transitions. So we assume that they have a conformation, this conformation, CO2 conformations is making this silver-silver transition bright, and it's increasing the intensity significantly. So we assume that because of that, it increases the intensity of the lowest energy peak, and also this intense starting peak is going down. So this is one of the reasons of forming this experimental result. And thank you, that's all.
Okay, well, thank Javid. Are there any questions? Suggestions? I have one. There are so many models, and if someone is looking at it for the first time, maybe you may design a diagram. Remember in previous year ago, Sam Brown was making literature search, and maybe you know this paper as well. It's standard. On one axis it's maybe charge, on another is number of silver atoms, and then the thickness of a dot is whether it is bright or not. And then you can overview like 20 structures and tell.
Yeah, I have that figure, yeah. I put it on there.
Okay, let's thank Javid once again. And in the remaining couple of minutes, should be an update. There should be an update. 2 pages?
Oh yeah,
Okay.
I just put the other version of that thing on just as like a comparison, I guess.
So let me introduce Landon Johnson. It is really recent work, therefore there are no printouts.
Yeah. So, yeah, you know, not to beat a dead horse, but I'm looking at the boundary between perovskite and, I guess I changed it to polyoxotitanate because that seems to be a more appropriate name for the exact nanocluster that I'm looking at. So, yeah, I don't know, I've done the motivation enough times, I guess. So this was shamelessly just copied and pasted from Fatima's poster for now. So this is, I'm gonna redo that a little bit, but those are the equations that I am using, minus the K and the K prime. I'm not going into quite that much depth with it. Still not really super visible. So these equations are just the self-consistency loop for DFT. This is the correlation between 2 wave functions. So what you do is you look at one wave function at one time and another wave function at any other wave function or the same one at the next time step. So yeah, so this is your correlation. You're just looking at how much these wave functions overlap. Then we use that to populate our Redfield tensor. We're using the approximation that your autocorrelation functions die extremely quickly, so we only really look at one time point, so this integral disappears and you only really have this term right here, no integral. So that's essentially these two end up going, I don't know, I would have to look at this more in detail, I guess, but essentially this is what the Redfield tensor is populated with under the approximations that we're making. And then these equations are how we model the time evolution of the electrons and holes. And then we use these ones to solve for the lifetime, I guess, the relaxation lifetime. That doesn't seem like the right word, but moving on. So I might try to just draw up some schematics and put those here instead of this, but I am currently still trying to get that stuff to run on my computer. So for now, these are the models that I'm looking at, and these are their binding energies. I don't really know if, I can't think of a more appropriate spot to put them. If anyone has a better idea, let me know, because it seems a little out of place there. These are the chemical structures of these. Yeah, these should be right. I did these off the top of my head though, so I can't really guarantee that those are totally accurate. So the only difference between the two polyoxotitanate clusters are the orientation and the ligands on sort of the flat side of the nanocluster. So in the acetate model, they're both passivated by these isopropanol. Yeah. These isopropanol ligands, whereas one of them is passivated with hydroxyl ligands in this case, and these are the ones that are actually facing the perovskite here, whereas in this case you have the acetates kind of along the rim of your nanocluster, adjacent to your perovskite. So these are the density of states plots for these two configurations. In the hydroxyl case, we have a band gap of 2.62 eV, and we have a slightly larger band gap in the acetate case of 2.99 eV. And if you look at the HOMO and the LUMO bands, red being HOMO, blue being LUMO, you can see that you actually have a separated charge, or a charge separated state. Maybe would be a better way to say that.
Landon, can I intervene?
Yes.
If it takes you about a month to swap these little panels on the diagram, you can just swap all other figures and keep this intact.
Oh, I just haven't been working on this yet. This wouldn't take me that long. I've just been bricking my computer constantly trying to get the other figures done. Okay. So, okay, yeah, so then this is, I guess, a schematic of these two. Yeah, I suppose I might as well just flip them around. That'd be less work eventually, because I'm probably gonna have to redo everything anyway once I get all my new figures. So this one is the isopropanol, or the acetate, and this one is the hydroxyl. So these two are flipped around. So since you have a higher, didn't we figure out a good way to say this last time?
Top edge of the valence band?
Yeah. Since the top edge of the valence band is higher in the perovskite case, and you have a lower conduction band edge for the polyoxotitanate, then you end up getting a charge transfer after relaxation. Okay, so once you photoexcite and then it relaxes, you end up with a charge transfer state. Whereas in the acetate model, or isopropanol model, you have both of your band edges in the polyoxotitanate. So upon relaxation, you won't end up with that charge state, which is not ideal for solar cell applications. These are the absorption spectra of these two models. They look almost identical. The only difference really is just kind of the depths of these little valleys in here, or I guess the height of the peaks. So I marked right here. I don't know, there might be a better thing to mark here, but I just, for now, put the excitation that I'm going to be showing in this next column. These were chosen because they had the highest oscillator strength of all the transitions.
Did you double check the absorption spectrum?
I haven't done that yet. I guess because I mean this one was already recalculated from what I had before, and they still look the same, I guess, so I don't really know what exactly I would do to actually verify this. So my laptop has to use a different figure renderer for MATLAB, so this image comes out looking a little crappy, and I'm still trying to get these ones done right now. So another computer would really be great if I could use that to try to make these figures, because this does not look as nice. But so this figure is showing the charge density with respect to Z. So I've got these models put next to here just so that you can have a visual reference of where physically the charge density is located. So the brighter green color represents a higher electron density, and the darker blue and purple color represents a larger hole density. And so I guess, yeah, this one is still working on that for the acetate right now. It should actually have that running right now, but I don't. So then I've got these green figures that kind of show the same thing, except instead of it being with respect to where you're at in your Z position or whatever, it's with respect to energy. So, so these are both the highest oscillator strength excitations. I just chose those because they would probably be the most representative, or at least that would be my best guess if I can only do 2 of these. So you initially excited up to LUMO plus 13, and you can see a decent, I guess, relaxation rate. So once it gets to this point, the electron has fully relaxed, and likewise down here, the hole has fully relaxed. So this would be the excitation lifetime, I guess. And over here, you can see that the electron takes a little bit longer than the hole does. So oh yeah, it's just not showing up very well in this light. So I basically cut out all of this stuff in the hydroxyl one, so I've got figures now that look more like this. Do these labels for my indices make sense, I guess? Is it kind of like clear what it is that I'm representing with those?
Yeah.
Okay. So this is showing the electron dynamics as it relaxes. It's just showing you which orbital, or the occupations of each orbital at some particular time. So as time goes on, you can see that it kind of transfers down into lower energy orbitals and ends up in the LUMO eventually. And I'm gonna change these to be more like LUMO plus whatever. And this is the same thing except for a hole. So you've only got your 4 states involved here, and it relaxes at about the same rate. And the same figure is just not as clean for the acetate model. Same thing, I guess. So this is a graph of the, so what I did is I took the 20 highest oscillator strength transitions, and I ran those calculations for all of those and calculated what the excitation lifetime would be in each case. And these are the results that I got. So these are the electrons in the hydroxyl model. Oh, and by the dissipation energy, what that is the absolute value of the energy difference between the initial excitation and the frontier orbital. So for the electrons, that would be whatever your excited state is, the energy of that excited state minus the LUMO. And for a hole, it would be the same thing except for the HOMO instead of the LUMO. So this is essentially how much energy the electron or hole would have to give up to return to the frontier. And I guess I don't really know how to plot trend lines for specific subsets of data.
Can you request help from Fatima?
I did, but I don't think that I made it very clear what exactly I was talking about. I don't really know how to word it very well, but yeah, I don't know how to do a trend line for just this and then just this, maybe
break,
ignore that point.
break the data set, break the file in 2 pieces.
Yeah.
One file for this data set, another for another data set, and just.
I guess the issue at that point would be that the legend would get very clunky and cumbersome and have a bunch of repeated entries. I don't know, maybe there's a way that you can tell it, don't include this or that, but I don't know how to do that off the top of my head.
How did you plot this graph figure?
This one is just from Excel. I put a bunch of stuff in a spreadsheet and tried to make a plot, so that seemed like the natural choice.
You can do in MATLAB, you can do.
What were you saying, Fatima?
How many data sets you have here? I saw different colors, like red.
I couldn't hear you, I'm sorry.
How many data sets you have here?
4 of them. So I've got the excitations for the electrons in the hydroxyl model, the holes for the hydroxyl model, the electrons for the isopropanol model here, and then the holes for the isopropanol model right here.
So what you can do, you can click on that. I see that there is a data set, blue points.
Yep.
So if you click over the blue one of the blue points, right click.
Yep.
Then you will see a couple of options. One option is add trend line.
Yep.
So you will select that one. And it will see different options.
Because I mean, this is a trend line for all of the blue data, but what I would like to do is make a trend line for just this subset of the blue data, and then just this subset of the blue data, and then likewise just this subset of the gray data, just this one of the yellow one, just this one of the yellow one, you know, maybe just this one of the orange one, or I could probably do the whole thing, but. Well, yeah, the orange one wouldn't be so bad just to do the whole thing all in one shot, because that's fairly linear, but the other ones are segmented chunks of being linear instead of.
Or I think this first, I think 3 sets of data, between 0 to 0.8.
Where at?
Dissipation energy, 0.8. Yeah. They are different from above 0.8.
Right, yeah.
So I think you can make 2 different plots then.
Okay.
Yeah, then you can. And if you increase the y-axis, suppose instead of 3 you set 5, then these data points will be closer.
Yeah, I guess I tried to zoom in as much to show as much detail as possible. But yeah, up in this region at least, the electron excitation lifetimes are not exactly organized.
It's scattered.
Yeah. There doesn't really seem to be much of a trend here at all. But there was one particular excitation that was unstable in the code, so some of this could be an artifact of that. It might just be due to instabilities. I don't really know.
You are the only participant in the conference.
Okay. But I suppose I could mention that it seems like there's a longer excitation lifetime for the acetate electrons up until a certain energy point.
Your call will be disconnected.
Although I guess I don't really know what happens up here in the acetate model, because none of those were.
I'll bring it up. It's possible.
But yeah, like I said, the data came from the 20 highest oscillator strength excitations in each case, so there just isn't really the data there for that right now. But you can see that the whole lifetime in the hydroxyl case is a little bit longer. And then, yeah, kind of same conclusions as before, except I took a couple of them out because those were not based on the right data. But yeah, they seem fairly comparable. Really, the major difference between these two models is the band structure at the edge. So that kind of seems to imply that the hydroxyl model would be more favorable for solar cell applications. And then I guess man, those do not show up very well. In addition, basically I have the same plot. This is exactly the same plot as I put on the, like right before the conclusions. This is just the relaxation rates instead of the, so this is the relaxation rates instead of the charge carrier lifetime. So it's just, they're reciprocals of each other. I'm kind of leaning towards using this one because that seems to use the space better, but if anybody has any good ideas for what I could put in this big blank white space over here, I'm open to ideas.
Use log plot and then white space will disappear.
Yeah. Yeah.
That's it?
Yep.
Well, thank Landon. Any quick questions or suggestions?
Why is your binding energy negative?
Don't worry about it. I'll change it.
I guess, yeah, whenever you see negative binding energy, that kind of implies it doesn't want to be binded.
Yeah, no, I just subtracted the one way and like typed up an email real quick with that, and then
So it's
just
just
copy
your
pasted like 20 minutes ago.
So it is your definition. Like the more negative, the stronger it binds.
Yeah.
Okay.
But yeah, that I will change that for sure.
More questions? Okay, we had some suggestions and questions during the talk, and they will be recorded so you can listen for the feedback. Then let's thank Landon and all speakers once again. So it would be really great if you complete posters tomorrow. Tomorrow is the last day when specific grant can be charged for printing. It's still, there are chances to print later, but tomorrow it will be much easier. Follow the suggestions from Jabet. He seemed to send email to everyone. And if you're not 100% sure, you can quickly send latest version to whoever is your primary advisor, but just plan on completing it. Okay, and we will have the last meeting before going to the conference on Friday, but there will be no posters, only oral things, because posters should be ready by then.